Rockets look clean, polished, and futuristic on the launch pad, but the truth is far more intense. Behind every launch is a manufacturing process filled with heat, pressure, precision, and split-second decisions where even a microscopic error can destroy a billion-dollar machine. Inside Elon Musk's SpaceX factories, rockets are not just built. They're engineered with an obsession for perfection and a pace that feels like controlled chaos. This is the full process of how a SpaceX rocket is made, from raw metal to flight-ready booster inside one of the most advanced manufacturing systems in America. Everything begins with raw materials, not pre-built parts. SpaceX controls as much of the process as possible, so the first step is transforming enormous aluminum lithium sheets and stainless steel coils into usable rocket structures. These massive metal rolls arrive at SpaceX facilities in Hawthorne, Boca Chica, and Cape Canaveral, where they're inspected, scanned, and measured down to the micron. This metal will eventually become the body of a rocket that survives supersonic winds, violent vibrations, cryogenic temperatures, and the heat of re-entry. Once approved, each steel section is shaped into cylindrical pieces using gigantic bending machines. These mills roll the metal slowly and evenly to avoid internal stress points. Even a slight bend that's off by a millimeter can compromise the entire rocket, so engineers monitor every second with laser alignment scanners. After bending, these giant cylinders are welded together using automated orbital welders, the same type of precise welding used in nuclear pressure vessels. Each weld is then scanned using X-ray imaging to confirm perfect structural integrity. But forming the shell is just the beginning. The real engineering happens when these segments start coming together. Large robotic arms and overhead cranes lift 30-foot steel sections like they're weightless, lowering them gently into position. Teams call out clearances, alignment data, and clamp engagement statuses in real time. The entire factory operates like a synchronized orchestra, everyone watching angles, tolerances, and heat zones during welding. One mistake can warp a seam or misalign a joint, so the alignment is adjusted constantly as the metal responds to temperature changes. Next comes the propulsion systems, the heart of every SpaceX rocket. Inside dedicated engine facilities, the Raptor and Merlin engines are assembled from hundreds of individually machined components. These are not simple engines. They're some of the most advanced machines ever engineered. Turbopumps spin faster than jet engines, combustion chambers operate at pressures higher than the bottom of the ocean, and the entire system must ignite and throttle perfectly under extreme conditions. Every component is welded, bolted, torqued, and scanned dozens of times. Sensors check fuel flow, pressure levels, metal fatigue, and microcracks. Engineers run constant stress simulations to identify weak points before they become failures. Once assembled, each engine undergoes brutal static fire tests at SpaceX's McGregor facility in Texas. Engines are bolted to massive test stands while firing at full power, producing fireballs, shockwaves, and noise heard miles away. Only engines that pass every test are cleared for installation. With the engines ready, the rocket's internal systems begin installation. Wiring harnesses, navigation computers, telemetry modules, pressure sensors, fuel lines, and valves all snake through the rocket's interior. SpaceX builds many of these components in-house to ensure rapid iteration. Technicians mount avionics modules carefully, securing each connection to survive launch forces. Tanks for liquid oxygen and super-chilled fuel are fitted next, each tested for pressure integrity using massive cryogenic chill-downs and hydraulic stress tests. One of the most demanding steps is tank integration. SpaceX rockets rely on cryogenic propellants far colder than Antarctica's lowest temperatures. That means the tanks must handle extreme contraction without cracking. Engineers chill tanks with liquid nitrogen during test cycles, watching how the metal behaves and searching for any anomalies. Sensors record every pressure fluctuation, every temperature dip, and every deformation pattern. Once tanks, wiring, and structural components are complete, the stage stacking process begins. Huge cranes lift completed rocket sections, first the aft section, then the middle dome, then the upper tank. Teams coordinate every move, checking alignment from multiple angles. Locking clamps, torque measurements, and sensor data guide the process. When the sections click together, the rocket begins to take shape for the first time. Next comes grid fins, landing legs, and aerodynamic surfaces. These components must survive re-entry temperatures approaching thousands of degrees. Each fin is CNC machined from a solid block of titanium, practically indestructible under normal conditions. They're mounted with precision torque and tested for movement accuracy. Landing legs undergo hydraulic compression tests, simulating touchdown forces. Now the rocket is structurally complete, but not yet flight-ready. It must pass through a phase of exhaustive testing. The rocket is placed on a transport mount and moved slowly and carefully to outdoor stands. Engineers run pressurization tests, scanning for leaks or weak welds. Fuel lines are chilled again with ultra-cold propellant to mimic real launch conditions. Every valve is opened, closed, rechecked, and stress-tested. Software teams upload guidance algorithms while monitoring thousands of telemetry readings. Then comes the biggest pre-launch test, the static fire. The entire rocket is filled with propellant, anchored securely, and ignited for a few seconds while firmly attached to the ground. The goal is simple: prove the rocket can survive the same stresses it will face on launch day. Vibrational loads, engine pressure, thrust balance, turbopump behavior, and thermal response are all analyzed in real time. A rocket that fails even one requirement gets rolled back for repairs. If the static fire is successful, the rocket is cleared for transport to the launch pad. This is a delicate operation. The rocket moves at walking speed as convoy teams check every inch of clearance. At the pad, hydraulic arms lift the rocket vertically, while engineers confirm alignments from all sides. Mounting clamps engage one by one. Umbilical lines connect fuel, power, and communication systems. Pressure readings must stay stable across thousands of psi. As launch approaches, the rocket undergoes final inspections. Every sensor, every valve, every circuit is double-checked. Propellant loading begins, chilling the tanks and building internal pressure. Engineers watch oxidizer levels, temperature fluctuations, and structural changes. A slight spike or dip triggers immediate review. Telemetry teams track the rocket's guidance systems, ensuring internal navigation is precise. When the countdown reaches its final minute, the entire rocket is alive. Fuel is boiling at cryogenic temperatures. Pumps are spinning, valves opening and closing, and internal computers taking over power management. The flight computer checks hundreds of parameters per second. If the rocket deviates even slightly from its expected behavior, the system automatically aborts. But when everything is green, every sensor, every engine, every pressure and alignment reading, the clock hits zero. Engines ignite with a violent burst of fire and shock waves, pushing millions of pounds of thrust downward. The clamps release, the strong back retracts, and the rocket rises, piercing the sky at thousands of kilometers per hour. Inside the control room, engineers monitor structural loads, thermal changes, vibration spikes, and pressure curves. When the rocket passes max Q, the moment of peak aerodynamic stress, they verify everything remains stable. The booster separates, reignites for return burn, flips back toward Earth, and uses grid fins to steer through the atmosphere. Landing burn ignites, legs deploy, and the booster touches down with precision that once seemed impossible. Achieving orbit is only half the accomplishment. Bringing the booster back safely allows SpaceX to build rockets faster, cheaper, and with more iterations. Every recovered engine, every repaired weld, every captured piece of data feeds back into the manufacturing process, making the next rocket better than the last. And this is why SpaceX builds rockets the way they do: fast, iterative, and obsessively detailed. Every sensor reading, every weld scan, every pressure test contributes to a system that transforms raw metal into reusable orbital-class rockets at a pace unmatched anywhere else in the world. If you want more breakdowns of advanced engineering, make sure you like, subscribe, and stay tuned for the next deep dive into modern technology.